Okay, my friends, get ready. This is going to be a trip. Albert Einstein says light is a cosmic speed limit. You can't go faster. It's just going to go the same speed forever. So no matter where it comes from, it never goes slower than the speed of light. That's completely wrong. Light can slow down, light can speed up. And I show that in very, very great detail. And I also have the new atomic theory, which is dipole electron flood theory, which creates the nucleus of atoms as dipoles. So the nucleus is not one big positive with a few neutrons in there. It's all dipoles, which means it's positive and negative little particles together. That's why it's 6 together. They have never been able to account for anything, not even gravity. Dark matter, where's all the weight of the universe going? They have no idea about any of this stuff. And it's because the atomic models are wrong. So if you look up AI and you go into AI or any of these mainstream, it starts off with an incorrect beginning point, so you're never going to get anything correct in mainstream physics. It's not going to happen. And the same thing, it carries over into everything else. It carries over into biology, into the body chemistry. It carries over into chemistry. We're going to have to change this. This has to change. It's not right. These aren't just big, gigantic particles. Hydrogen is not one big proton and one little electron. It's 1,825 dipoles. I'm going to show all this in very, very great detail. And there's no more reason to not discuss this. There's so much detail. I'm going to show you right now. If you could just fight me back on this, fight me. And Professor Dave, some guy that's claiming, oh, I can explain everything, and he will debate anybody, debate me, my friend, because I am waiting for you. And I will destroy you. If you think you can debate me and win, you got another thing coming. Because I use evidence. I don't just talk about sporadic, crazy things. I'm talking about, here's what happened, and here's what the result was. Explain it. And if you can explain it better than I can, God bless you, which is something you probably don't believe in. I don't know. Okay, my friends, this is going to be a lot of fun. This is my interpretation of a proton and a neutron. A neutron just has one more particle of these than the proton. Now, let's go and see what they have to say about this in science. All right, this is the standard model of particle physics. You see how here they got pluses and neutral charges? That's what makes up an atom. All right, now this is a nucleus. All right, there's protons and neutrons in here. The pluses are the protons. The purple ones are just neutrons. Now, these out here are supposedly the electrons. Well, that is not my model. Mine is a complete ball of dipoles. And that's the only way it would work. There's no reason that these would stay out there. They'd be slammed right in here instantaneously. Nothing works. Nothing in the atomic model works. They can't explain isotopes. Isotopes, you take one little tiny bitty piece off of there and it changes. And you can change an isotope from one atom, can have 20 or 30 different isotopes easily, but it actually has many more. Anyway, this doesn't work. The atomic dipole flood, dipole electron flood theory, this is my theory. Instead of having what they show is a big gigantic proton and neutrons and just a few electrons, there's dipoles, and they're all dipoles, but when you put them in a nucleus, they can separate and push the black part to the center. Dipole means there's a black and a white, and they push the black to the center and surround it with the white, and that's all we ever see is white, and that bounces back at you. That's energetic. That's why we've never seen the dark matter. It's in everything you got. Everything there is has dark matter in it, even light. All right, if you're any kind of a physics geek, you've probably heard of the strong nuclear force, maybe even the weak nuclear force. Well, what does that mean? Well, the nucleus is the center of the atom, the core, the nucleus. And then they have little electrons. They don't even worry about those. Well, what's inside that nucleus? Why is that nucleus held together with these particles like that? What holds the protons and neutrons together in these periods, in these stable chunks. They have a certain mass. But they're only stable to a certain degree. You have a ton of isotopes between every particle, and I mean a ton of them. So they're not really as stable, and they can't account for isotopes given the standard model. It just doesn't work. So they say they found a milestone unraveling the universal fundamental forces at the Large Hadron Collider. Now, I am going to tell you exactly what they found, and I don't think they know what they found, but I do. And I will tell you that. And I know it sounds arrogant, but if it's true, it ain't bragging. This is just extraordinary. The primary purpose of the Large Hadron Collider is to explore the fundamental building blocks of matter and the forces that govern them. Fundamental, that means the tiniest bits of matter. They say they found a milestone achieved in unraveling, and I'll show you what they did find, in my estimation. We'll come back and look at this in a minute. All right, here's AI. AI says that I asked, is light the smallest particle? AI says yes. Photons are the smallest possible particles of light and electromagnetic energy. So they're the tiniest thing that exists. They're also known as quanta of light. Photons are invisible and have no mass or charge. Not correct, AI. It allows them to travel at the speed of light. They can also exhibit both particle and wave-like properties. That is correct. Depending upon their position. No, depending upon if they're moving through the air, they're going to create a wave as they force, and I will show that. For example, photons carry electromagnetic, that's a big ball of magnetism, which is a force field. So a photon carries a force field of force between electrons and an atom's nucleus by attracting each other. No, that's just not right. It's a big ball of dipoles. I will show you. Photons are also responsible for carrying images to our eyes when we read something on a page or a screen or look at anything. Anytime you can see light coming back at you, it means it bounced back. And it bounced back because there's a big round field around the photon. I mean around the, photon, yeah. And it bounces just like a basketball right back at you. The dark matter doesn't do that. We've never seen the dark matter. I will show you precisely why I can say these things. But don't forget, photons are the smallest particle that exists. All right, here's the answer to this question. Is laser light the same as just normal light? Is it like the same particles? Well, it is, but here's the difference. Laser generates a beam of very intense light, and it does it by using a crystal that vibrates exactly at a certain frequency. Now, the major difference between laser light and light generated by white light sources, such as a light bulb, is that laser light is monochromatic, one frequency. So it's coming out red or blue or green and that type of thing. That's it. It's not going to have all the colors together in a white light, because a white light is nothing more than all the colors together in one big ball. And we can separate them out, and we did. We can separate the green from the red from the blue and actually see them interacting at the same time. Now, monochromatic means that all of the light produced by the laser is of a single wavelength, which is fine. It's still light. Light is light. And they say that light is light, case closed. Monochromatic light is just one frequency of it. The full wave spectrum of light, white light, is all mixed together. That's no difference though. It's just all the frequencies are mixed together to get the white. Okay, so once again, AI is wrong. It says photons are tiny particles made up of electromagnetic waves. They're not just waves, they're actual particles. And they create waves as they push through all the particles in front of them. They have to push those fields out of the way. Let's get into the pictures. All right, I'm just going to give you the broad overview. This is a photon of light. And it's a pulsed red laser. It's called bip, 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 and these are photons. And they have to push through the particles of gases and so forth, which have fields. And they have to push their field through these fields. And these glow, and that glows much more because that's the one that's really pushing. Now, we accelerated that. That is just beginning to accelerate. That's the only reason you even see it. And now it's really starting to accelerate. And then right here, it goes into full acceleration mode and turns into a photon. All right, back here it's like what they call a neutrino. And it gets stronger and stronger and stronger. That means the flavor keeps increasing until it hits right about here. And at that point, it turns into a full-fledged photon. And here they are right down here. Now, I'll show you these better. But I think you can see that pretty good. These are neutrinos. That's the photon. The only reason you see that so clearly is that's dead in line with the Venturi. The other ones are not. Now, when they come out from the Venturi, because this is the Venturi, it sucks the particles forward very, very, very fast. And that's just what a Venturi does. It's not unknown. And at the Venturi, it's so restricted that only the white can get through. And you saw here, the black and the white. All right. At the Venturi, they break apart. And only the black can get through. I mean, only the white can get through and the black can't. And coming out of the Venturi this way, if we were looking into it, we see the Higgs fields. We're going to look at this a little closer in a minute. And these are the Higgs fields right here. And this is the blue light coming in real fast and slowing down. You see how it's closer here, and you can only see it looks like one particle. By the time you get to the other end, it slows down to where you can see how wide it is, and you can see there's two particles. There is two in every one, but the blue is just so fast. We don't use the blue for, well, we're not doing any experiments at all anymore. It's done. Rod Warren did all these, must have spent thousands of hours. Nobody paid attention for 10 years now. So, finally you have to sort of call it quits. I'm not of that nature. So, I mean, there's no denying this. It's just not deniable. Let me show you the particles and the electron flood theory. And CERN and all of them, they have the exact same particles. Fermilab, identical particles. All right, before I get into this too deep, these are the particles right here. This goes way, way back. And we were doing the same thing a little later than this, but very close. When I saw this article, I knew what it was, and I did contact Fermilab about this. Now, this is that black particle, which has a glowy edge around it, and has all the mass. This, they say, has no mass, and it has all the energy, it has a field. And I agree with this. And then they say the standard model is the most important model ever. And they claim that, standard model successful. No, not really. And then they say, talking to quantum foam, empty space isn't empty. That's correct. Light is a particle. And there's all dust, there's all kinds of debris in space. And here's the Dirac neutrino. And they either are fully in a neutrino phase, or they're in a sort of halfway, the Majorna, which is a neutrino. This is a fully fledged photon, electron, totally energized. This is like growing energy. All right, listen to this. This is really crazy. They are looking for what they call the weak nuclear force. Well, I'm going to show you what the weak nuclear force is, but here's what they do. They take these big protons. And when I say big, protons are the tiniest particle they think, and neutrons. So they got protons and neutrons. Here we got protons, we got neutrons. They send them around, back and forth, bam, they hit like this. But they can't do it very clearly. They don't necessarily hit head on. They might be scattering off here or there. There's all kinds of collisions happening, but very few, because they're using billions and billions of particles, and they might get 25, 30, 40, 50 hits on each one of these huge experiments. Now, what happens to these particles? These are huge compared to light, which is what we use, light. So these are actually, each one of these is a ball of dipoles. And that's what holds it together. And here it is right here in dipole flood theory model. Right there. So they're dipoles. There's a black and a white to them, yes. And they always put the core in the center as a positive. That's fine. But they only had a couple little electrons out here. That's not true. The core is also made of dipoles. It's not made of just positive. So that's what holds it together. Now, you have different levels of stickiness. All right, the green, I mean the red, I'm sorry, the black goes right to the center. Can't stop that. They don't care about being touching each other. They couldn't care less. And the white comes swarming in. The white is always, 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 always a strong nuclear force. But it depends on where it is in the ball. So the red ones are not attached real well because they're, you know, kind of floating around. They're on the outside. Here's what the thing really looks like. All right, you see this here? It's just exactly the same as this. The black stuff, which is the dipole part. There's supposed to be those dipoles I showed you a second ago here. Make sure that you understand. They're supposed to be like this, the black and the white together. The same as Fermilab has, no difference whatsoever. But they're supposed to be stuck tightly together, and they are. Now, this one side of this, or the other, they're both actual electrons. We always thought the electron was only the glowy part. Not true. An electron has a dark side. So every electron has a carrier. They used to call it the carrier boson. I don't know what happened to that. But it carries the electron. That's true. And I'll show you pushing the electrons in a second. Now, the one that's going through the air this way, you see these little white particles? You see them? Those little white particles are pushing against, well, that's pushing against them. And it makes this thing glow. And as it glows up real strong, it'll flip. And that one will come to the front and start to charge up. This one's being protected, so it's getting dim. Now, only the white ones can change size. The black ones cannot change size. Nothing you can do to change them. They're the same size forever. And they don't absorb, they don't reflect, they don't emit. And it's dark matter. But there's a weight to it and a stickiness to it. And that white wants nothing more than be attached to that. So that's why you get them in a ball surrounding the dark matter. So here they are in that ball right here. And inside, and of course these are all different colors, but they're not going to be. The red ones have a certain energy charge to them because they're that far away from it. It all relates to dipole moments, which means the distance you are away from the center of charge, basically, determines the dipole moment. So these don't have a very intense dipole moment compared to the green, which is much stronger. The blue is like off the charts. So when you explode this and it hits, boom, and they go flying, most of the times you're going to get a lot of the red is going to go, and it's not going to be the blue, because the blue is like a head-on total collision to get right down to that core and to knock that black ball right out of there. And then, yes, you can get some blue coming out of here. That's not normal. So they normally see the red interacting around, banging around, but not going that far because it's just getting bounced off. Let me show you what they do see. All right, this is obviously not the right thing. But here's the situation. The red ones being way on the outside, when they get banged, they sort of go out a little bit and come back. So they see a lot of that. And whenever they see the blue ones, they go and they never come back. Because when you smash way down into the core, that's it, they're gone. And the yellows and the white, same thing. But the red is so far out on the periphery that it just sort of wobbles around out there and comes back together. Because they're not hitting head on. If they hit head on, you get the blues. All right, if they hit like this, you get a bunch of red bubbles around it. That's about the best I can do on that. Okay, here comes the Tour de Grande. This is the pulsed red laser. All of these little particles are extremely agitated because they were just having a nice day. Everybody's just getting along with each other, and all of a sudden this guy comes through here, says, "Get the hell out of the way." Everybody fluffs up. This guy gets really mad. I call it push to shove. They shove back, they push through, and this guy wins every time. He's coming through. Now, so we got that. And what happens in the case of a Venturi? That's acceleration. It's already starting to accelerate. Here's true acceleration. Remember the wave. I know you saw the wave. Now, we were about somewhere about here, and we could just see it starting to accelerate. And that's why it was starting to glow. And it wasn't warped like that yet, to speak of. Let's go back and look at it. Let's not make any rash decisions here. It's not warped yet. It's just beginning to accelerate, and it's going to fold its magnetic field in, because it's going so fast that it's just pulling its magnetic field through those particles and crushing it. I mean, it's just stunning what it's doing. Look at this. Look at that. It's coming through here, and now we were somewhere back here where it was sort of just a wave. Now it's starting to bend, fold in, and it's completely folded in here, and the particle is just like a rocket. That's acceleration. There is nobody in their right mind can tell me that's not accelerating. You can see the wave. It's just pulled forward. There's nobody can deny that. The only people that can deny that is if you have a PhD in physics. Then you can deny anything you want, because that doesn't. No. Einstein says it can't accelerate. No. And lights a particle. No. The wave. They're going to go on and on and on because of laws and constants and theorems that have always been, standard model, this model, that model. Well, this is the new model, and it's dipole electron flood theory, and that is a dipole electrons back to back make a photon. A single dipole electron is literally an electron, and those will burn you. And electrons create static, they create lightning, they're excessive electrons, they create heat. Excess electrons is heat. And they have weight. And I'm going to tell you this is a fact. No question whatsoever, 100% certainty. When something is a solid material like this, and you get it hotter, it will be heavier. Right? It will be heavier. It won't go up like a hot air balloon. It will be heavier. And the reason is you're adding electrons into here. Electrons have a weight. Every electron, I believe, weighs 0.0005854 or something like that, atomic mass units. So they do have a weight. And the hotter it gets, the heavier it gets. And then when the electrons bleed out into something that wants to accept them, it gets lighter and comes back up. And I know this, no question whatsoever, 100% fact. I worked with weights and measures, and I had to get calibration weights certified. And when you went up to do that, they had to keep them for 24 hours to make sure the same temperature. Otherwise, they wouldn't weigh right. And they didn't know what then. I said to myself, how could that be? I said, why can't you just do it now? He says, no, you got to leave them here 24 hours. And I said, well, for what? And he says, they got to be the same temperature. And I said, come on, for why? And he says, well, nobody knows. We think it might have something to do with air currents, but you can't do, there's nothing you can do. You have to leave them here. And that's a law, so case closed, so I had to leave them there. Anyway, that's how I know. And it is a known fact, so that's just a fact. Okay, anytime you have acceleration, it's increase in energy. Anytime you have luminosity, glow, gets bigger, it's energy increasing. There's no dispute to this. We started back here, you could hardly see it. And all of a sudden, it got brighter than hell. And that, my friends, is a sub-nuclear explosion. Oh, come on, Roger, sub-nuclear explosion? Yes, 100% certainty. What we started with was those two particles together. They are nuclear particles. They build the nucleus. Those are the dipole electrons that build the nucleus. All right, when you excite an atom to a point where it gives off the electron, you're sending these out. Little bits and pieces. You're not sending these things. Well, CERN's doing just the opposite. They're doing huge things. And then they search through literally billions of collisions. And what they're finding is this weak force is not a weak force. It's this thing right here. It's the red way out on the outside. And it's just an almost collision. So instead of hitting head on and getting these real heavy duty flyers, they're hitting like this and just sort of pushing around the red one out on the edges. But if they hit right in the center, everything goes. See, this is a CERN, where they're colliding these gigantic particles together and getting all this debris goes flying. And they see the circular patterns. Yes, absolutely going to see that. But that's mostly from the red. They're not going far enough to get away. And they sort of circle back into position and come back together. Now, this is primarily what they see. Is when they hit, they get chunks like this. And X means a gigantic whatever. It could be that size, it could be this size, it could be that size, but it's not going to be any of the tiniest primary particles. These are the primaries. X means just means a chunk. Now, that is a photon, and these little ones are the electron and neutron, they're the dipoles. But sometimes they see them real energetic, sometimes not as energetic. That's why they show them little or big. They really don't know what they're doing, I got to be honest with you, because what they're talking about here is they found a weak nuclear force. It's not weak nuclear force. They found the red particle by looking through billions. Well, let me see. Let's look to see what they say. I don't want to make any false claims. All right, this is their primary purpose of the Large Hadron Collider, is to explore the fundamental building blocks of matter and the forces that govern them, which is light. This is what I'm talking about. Now listen to this now. It says, building upon this understanding, physicists in the 60s discovered electromagnetism is connected to another force, the weak force. Well, they didn't know it was anyway, the weak force operates within the nucleus of the atoms, inside the ball, which is the nucleus. And then they think there's a couple of little things floating around, which are electrons. Now, this revelation led to the development of the Electroweak Theory, which is not correct. It says that electromagnetism and the weak force is actually low energy manifestations of a unified force called the unified electroweak interactions. Well, it is, it's actually not that far off now that I'm actually thinking about it, because they're saying it is the Electroweak Theory. And they're saying there's electromagnetism, and a weak force is actually low energy manifestations, basically, of a unified force of the same thing, called the unified electroweak interaction. It's not weak, though. Key discoveries such as the Higgs boson have confirmed this concept. Well, yes and no, because you can get different colored Higgs. You can have, and actually that's what they are. You know what? I'm seeing this in a different light. Look at what they did. They're seeing these different interactions. And they realize they have different energies, but they're coming from the same particles. I think they must understand they're coming from the same particles. They just don't realize the particles are dipoles. And they don't realize the structure of the atom. That's my take now. See, you learn something if you keep your eye on the ball here. And don't forget, this is Fermilab. And this one has all the mass and is a pusher, and this one is just a glower. This is burns you. This one here just pushes you out of the way. And it does. Here it is right here. You see that? That's through the Venturi, but not all the black is restricted. You see how the black is coming through here? Pushing the white out of it. And this is the true field, the field's pulsation. These are Whistler waves, and that's because it's only being affected by the white. That's why these are so wide and these are so tight. And the more black you have back here, the tighter they'll get as well. And the more white will come out here, and the Whistler waves will go more into the Whistler range. There's a lot of activity you got to think about here. And here's the red and the green at the same time through the same Venturi. This was Fabien Brulé did this. Or most of the, well, just about everything else Rod Warren did. I did a little bit here and there, but nothing like these guys. And this is the green pushing the red right out of the way. Same particle. As I showed you, or will show you. Here's the red. There it is right there. There's the red. Now, it actually separates the black from the white. I did show you that, or I'll show you again, because I think maybe I didn't, or I didn't do it well. I do both of those things. Now, there is the neutrino phase coming, and these are neutrinos too. They're only going at a little bit of energy because of the pushback. This is the one that's getting energetic because it's right in the, going to hit the Venturi. It's straight on line. That's why it's glowing much. And this is actually a photon. And the reason it's a photon, normally you don't get a photon until it starts bouncing back at you. It's a photon. The reason you see it's a photon here is because it thinks it hit a wall. And it thinks it hit something to bounce back from. And it did. And it will bounce back right here, because this is basically a wall. And here's the wall right here. Bam! You can't get through the Venturi, the black can't. So the white squirts through, and the black bounces back out. This right here was the wall. Well, actually it's right here. And the whole thing is exploding. You see all these? Those are other particles that are in the air. You don't see them because they're just not being pushed back at, or they're not hitting anything yet. Well, now they're hitting something. They think they hit a wall too, all of them, because of this. All right, this is a subatomic nuclear explosion. Well, what is a nuclear explosion? The particles in a nucleus come apart. And what nuclear particles are they? Light is a nuclear particle. That's a nuclear particle. So if we divided that, that's a nuclear explosion. And it is also fission, and it is fusion on a subatomic level. Here it is right here. Subatomic nuclear explosion. Fission and fusion. That's a nuclear explosion. When it came in here, it was those particles attached together. Here the black doesn't all go, nothing goes through. The black did not go through here at all. You can make different Venturis and tune them different ways and have different construction of them. But essentially all it is a restriction. So that all of these fields have to crush through that one little tiny slot. So you're gathering them basically into a crusher. Because the black can't get through. So the black keeps smashing, because we know the black pushes the white. There's no question about that. You say, well, how do we know that, Roger? It looks like they're pushing through there. No, I can see them, and you know, and I just showed you. They push the white. You see them? The black pushes the white. The white just not taking off by itself. The black is pushing the white, and it's just squirting it through the Venturi over here. The same thing. It's these are pulse, bam, bam, bam. And the white can squirt, but the black can't get through. It's like slapping it with a paddle. And the white squirts through. And it is called fission and fusion. And the muon neutrinos, which was the black one, turns into just a black sterile muon, they call it. And the electron neutrino, which was the white one attached, does the shock. And that's where you get an enormous amount of energy. There's no weight to this right here. There's no weight. Almost all the weight there is in the universe is the dark matter. And it carries the white with it. This has no weight. And I can tell you something. Listen to this now very, very carefully. This is electricity. And you say, oh, Roger, how could it be electricity? Well, here's how I can tell you exactly why. All right. Let me just show you something. Hold on. Okay, this is from a channel called Evolving World. And he says, does a fully charged battery weigh more than when it's empty? So we're about a minute into this. So here we go. Listen to this.
Pack, and we are currently at about 15%. I think that's probably closer to 14. What we're going to do, weigh the car right now, and then afterwards we're going to charge it up. And then I'm going to come back when it's 100% fully charged, and then we're going to weigh it again, and we're going to hopefully answer the question. Okay, so here it is on the scales right now. as you can see. And this is how much it weighs as it sits. We're looking at about 3492 or so. So now is the time to place your bets, make your wagers. Is it 10 pound, 5 pound, no pound? Don't know. But anyway, we're going to go ahead and find out here. Let's go ahead and plug her in. This is probably going to be a 6-hour experiment. I'm just going to leave that thing plugged in.
All right, so he just said, think about it. What would you think would happen? Let me tell you something right now. Gasoline. When you put gasoline in your car, for every gallon it weighs, I believe it's right around 6 pounds. So if you put 10 gallons in, you would add 60 pounds to your car. All right? He's filling it up with electricity. It gives you the same mileage. You could drive, it's got the same energy as a tank of gas, only it's electricity. How much does the electricity weigh compared to the gas? Okay, so why do I say that is raw electricity right there? Well, because I'm telling you right now, that is energetic as hell. Whenever you see something brilliant like that, that's extreme amounts of energy. And the other thing is that it's separated from that black particle. All right, so you know he's putting electricity in here. Well, what is electricity made out of? First of all, we're going to find out, does it weigh anything? I'm going to show you something right now. Here's electricity right there. There it is right there. That's electricity. And I can prove it in a number of ways. But let's go back to the weight. Does it weigh anything? Let's find out. All right, so here he goes. He's going to charge it up. It's way low.
And
it weighed 3,492
about 7.5 hours later here, I just turned the car on. We're getting very, very close to being 100% here. So for all practical purposes, we're there. I'm going to go ahead and show you what our weight is. So this is a last call here. So what do you think it is? 10 pounds, 5 pounds, no pounds?
Remember, I believe we started with 3492. I'm sure he's going to reiterate it, but what did you come up with? Don't forget, you put 10 gallons of gas in your car, weighs 60 pounds. To do the same job as what he did with the electricity. Now let's see how much it weighs.
Well, here it is. That's kind of interesting. Not totally surprised, but then again, there's a part of me that is a little bit puzzled by that. So basically, 0 pound difference here. Makes no difference whatsoever. I think that's what...
No difference whatsoever. So you charge it or discharge it. Well, how did you get all that energy? Where did that come from? I can show you where it came from, and I can demonstrate it in a couple other ways. All right, first of all, these are the Fermilab particles they found in their lab. Let's talk about what they say about these. This one is a fixed particle, never changes size, and has all the mass. This one is abstract, has no mass, but it has some kind of a field. Now, this is exactly what they say at Fermilab about those two particles. There they are right there. This is a Fermilab particle. It's not me. And what do they say about those two? This is the fixed particle. That's the point particle. All right, let's just sum it right up. In summary, the extended particle, which is the fixed one, has a fixed size, never changes. It has a fuzzy edge around it, yes, which that's the color of the other particle. Now, the point-like particles are mathematical abstractions with 0 size. We just filled up that car with electricity. It didn't gain any weight whatsoever. That's because that part it's an abstraction. I can't account for it either. All I can think of is like some kind of like a soap bubble that's just so fine that there's no weight to it to speak of. I mean, it appears that there is no weight. I can't, and I'll show you why I can also say that in the atomic bomb blast we can actually see this. Now let's just finish this up. He says The extended particle is the fixed black one. It has a fuzzy edge around it. The point particles are just nothing, they're zero. But they have a field surrounding them. Now, something's strange with that. I can't account for that, but I do know that that has no weight and has all the burn, and this has all the weight and no burn. And I'm going to prove that right now in an atomic bomb blast. All right, I'm going to show you an atomic bomb blast, which was a test. They wanted to see what would happen to this house when they set off the atomic bomb. Now, here's what's going on with an atomic bomb. Normally, way up here, in these heavy uranium, plutonium, all up in here, you have a ton of these particles. So down here, let's say that is hydrogen. This is going to be like thousands of times bigger. Hydrogen is 1. Uranium, hold on, my glasses don't work all that well. Uranium is 238. All right, so it's 238 times bigger than this is uranium. Now, then they enrich it. And what they do is they force more electrons in there. So there's more electrons. I believe that's it. Or they might force more protons in there so that it's even, yeah, I would think they force more protons in so that it's a bigger nuclear mass. You hear that? Wrath of God. So it's getting bigger and bigger and bigger and bigger and bigger. Now, they make it so big that it's just totally unstable, and there's just so many particles, it's just unbelievable, and they're just enormous, and they don't want to stay together, first of all, and then they compact them magnetically and with other materials, and then they explode them inward, and when they go out, the first thing that comes out is the white particles, all these particles, which are the ones that burn and glow. But they have no mass. They have no mass whatsoever. I cannot account for this. They're moving. Something's moving there. Because the house burns up, but I'll show you. It's just, I still can't account for it. But something is moving. There's no question whatsoever, but it's not pushing. This is, it's a phenomena I cannot explain. All right, so you understand that's what it is. It's a gigantic ball of electrons. They force in, and when they go out, they burn everything, and then the black particles come behind them and knock the house down because they have the mass. These have no mass. They burn. This comes behind and knocks the house down. All right, this is from atomcentral.com. They got a truck up here delivering all this equipment, setting it all up for this test house. And then they have a hardened enclosure back here. So the bomb blast is going to push against the outside of it. It's not going to hurt it because it's a hardened enclosure. And the camera is facing this way, so that it's not going to hurt the camera lens either. So they're going to watch what's going on. They're going to drive the truck out of the way, and so the truck won't be here. Anyway, these poles and these wires and these shingles and everything here that's combustible, everything that can combust, will combust, and it'll just rise up like fumes. I got this on extremely slow motion. The bomb is going to go off, so you're boom. And the first thing is, this will give brilliant, brilliant, brilliant light. You won't be able to see anything. There'll be so many white particles in here. And then everything will just start to smoke. But nothing got pushed. Nothing got knocked over. Nothing got pushed. Even the smoke doesn't get pushed. Watch this. It's stunning. For me, the first time I saw it, blew me away. So here it goes. I don't think anybody's ever paid attention. That's it right there. Look at this. You saw the first part was the flash, and look what's going on. It's still burning. I just stopped it. The first part was the flash. Look at all the wires. Look at the poles. Look at the house. The shingles burning, everything that was facing where those electrons could invade, and they have no mass. They're not pushing anything. Nothing's moving. Explain that one to me. Now, they're not hitting on the side, so the side doesn't get destroyed, and they're hitting metal here, and metal doesn't burn up like anything combustible. It's combustible stuff, just so it's absorbing electrons, because combustible means it can absorb electrons and fume and destruct. And this is what you call fume and destruction. So now pretty much the black is starting to catch up. And watch what happens when the black hits. It's all over. Sayonara. Boom. That's the black part. That's where the weight is. The others didn't do anything. It just smoked it. It just smoked it. This is not smoking. This is pushing. And I'll bet you if you could tell the temperature difference between here and when the first particles hit, it would be just staggeringly different. I think this is like literally almost absolute zero, just for an instant, after extreme amounts of energy, which is a high energy. You hear the lightning, thunder and lightning going off? When we first moved into this house, I had this house built, and I put up all kind of things, you know, wiring in the attic and so forth that were for security lights and alarm and all that stuff. Within about 2 months, we got hit by lightning twice. So I had the lightning rods put in, and they worked, never again. And they put in 10-foot copper rods, both ends of the house, and run copper rods all the way to the top across, the chimney, everything. And it grounds the house, so they can't build up particles that will attract the lightning. And the lightning doesn't hit it and it go to ground. It just doesn't, the lightning doesn't want to hit it because it's not attractive to it. All right, this is still in dispute, to be perfectly honest with you. Does a lightning rod prevent lightning strikes? And they say, yeah, well, I know it does, because my house, this goes back 35 years or so ago when we had the house built. Never once again, twice in the first month or two, we got hit by lightning. I'm up on a rise, so it comes up pretty steep, and then my house is here, and it's very tall, and it's when it's swept up, boom, it would charge the house up. Now the lightning rods allowed the dissipation of it. This is what this one guy says. Anyway, listen to what it says. The one guy says, I was always under the impression a lightning rod worked to protect a building by being the tallest part of the building, having a low path of resistance to the ground. So it would go through that. You'd still get hit by lightning, but it would be easy to go to ground, thus being a good target for lightning to hit, reducing the chances it would strike elsewhere on a building. Never been hit once again by lightning, or anywhere around the house. However, when reading an Ars technical article, which I'm going to look into in a second, one comment from the user said the theory is incorrect, explaining a lightning rod actually prevents lightning strikes in the first place. Exactly. And that's what they told me when they put it in. They said, no, I don't listen to that. You're not going to get in anymore. I said, how do you know that? I said, why would you put them in? He says, it stops the lightning from being attracted to the house. Now, I have copper, 10-foot copper rods, and I have copper coming up all the way across and tips coming off of the top part of my house, which is off the chimney and off a few on the roof line. And it never happened again. So he says the lightning rod, it says lightning happens when a really huge negative charge builds up in the ground, corresponding to a positive charge overhead. The differential becomes sufficient to jump the gap, which is lightning. And as others are pointing out repeatedly, air is an excellent insulator, so it takes whackingly huge voltage difference to make the arc. Yes. Now, a lightning rod doesn't exist to provide a spot for the lightning to strike. Rather, it exists to dissipate the charge. So there's no charge up there. To take that charge so that the strike never happens at all. It comes from early experiments with Leyden jars. If a pointed metal rod was attached to the jar, it wouldn't charge. Right? It couldn't take on a charge. The electrons are able to leap off of that pointed tip into the air, dissipating charge as fast as it accumulates. So you couldn't charge. My house can't get charged up. The lightning rod does the same thing. on a larger scale. It spits out electrons into the air like crazy so that the charge won't build up sufficiently and the lightning never hits at all. And like I say, many, many years now, and never even the threat of a lightning strike at the house. And I tell you, it's scary as hell. Twice. And you burn your house down just like that. All right, I know I showed you the car not gaining any weight. It filled up. In a gasoline car, it would add 60 pounds to do the same as 0 in an electric car. So I claim that the white particles, which are these particles, are the ones that have no weight. Just like Fermilab says, they're abstractions, they have no weight. And you saw the house just smoke up because of the white ones, and then the black ones hit. And this is the proof that they do separate. And this is the nuclear explosion here, and the black one is pushing the white cloud ahead of it. The house is here, burn, 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 just smoking up, not going anywhere. And then boom. These they call Whistler waves. It's understood in nuclear physics. These are Whistler waves. They precede these waves, which are the atomic bomb blast waves. And the reason is that these are only waves created by the magnetic fields. It's just pushing the whites. And really that's why you see two completely different separations between here and here. And this is in the audible range. They call it a Whistler. Pop. And then this one comes in. Okay, we got a couple of issues here with AI. Photons are tiny particles. Yes, they are. They're made up of electromagnetic waves. Yes and no. The reason they look like waves is because they're doing this. They're spinning in a circle. And to the side it looks like a wave. This is a long wave, which would be red. That's green, and that's blue. Bzzz. Now, they say they all go the same speed. I'm not sure that's true. White light is all of these together in just a big beam of all these three particles at the same time. Now, they're the smallest. Photons are the smallest possible particles of light. They have no mass or charge. Totally wrong. They have a mass. The black is the mass. The charge is very strong when they're bouncing off of something, or when they're trying to fit through that venturi, extremely strong. So they have no mass, incorrect, or charge, incorrect. They can travel at the speed of light. Well, they are light. Photons are light. Photons are also known as quanta of light, and are examples of quantum, which is a discrete package of energy or matter. Yes, it's a photon. And it's that particle I show. Alright, so we know we started out with light. And light literally makes up everything there is, because light is made of these little dipole particles. And when you have 1,823 of these dipoles together, you have a semi-stable particle called a hydrogen. Or let's say 1825. And then the next stable one is helium. And that's 7,350 or something. Because every proton is 1,823 particles, and every neutron is 1,824. This only has one, so it's about 1,823, 24, 25, somewhere around there. Helium has 4. All right, because it's got 2 neutrons, 2 protons. That's what they claim. So that's like 8,000 almost. So they go up very quick. These are the 2 smallest particles that exist. When you get up into uranium and all that, you got hundreds of thousands. I think I counted uranium was 374,000, something like that. I can't remember. But all you got to do, well, take uranium as 238. So you take uranium 238 and multiply 2,000 times 238, and that's how much particles are in the uranium. And that's why they can do what they do. And it gives them all these half-lives. And what makes all these metals and things are bacteria using enzymes. Enzymes deconstruct and reconstruct molecules. It's called nucleosynthesis. All right, nucleuses being synthesized into something else. They don't just decay downwards, they can decay upwards. The daughter isotopes can go up, and they do. Right now they can only account up to iron, but now you can account up to forever, because they keep getting bigger and bigger. Now at a point, they're just so unstable they won't stick together anymore. But whatever your body needs, and we have uranium in us, you know. It's supposed to be in us. It's not there just by accident. It's not there because of contamination. And we have we do have, I believe, all of these transition metals, and they are the movers that move things because they have charges. And they're in the blood. They just did a survey of 26 different blood elements, which are metals, all the transition metals, and how much there is in each type of blood: plasma, whole blood, and something else. Now remember I said light spins, and it does. It spins just like this. And this is the slit coming through here, and some are way down here and some are way over here. But primarily they're going to go through the center. Once they get on the other side of the slit, they keep these patterns to keep each other away from each other. You see how elegant those patterns are? Those are pretty seriously divided little strips of light. Those are light. So the light is saying, you stay away from me, you stay away from me, you stay away from me, you stay away. And they set up these patterns. So light spins. Now, red is a slow spinner. It's way down like this. Green is much faster, and blue is very fast. And but they are the same particle. See, here's the green and the red. I probably showed you this, but that's okay. Here's the red coming in, and it just gets out of the way, and the green, and hits way back out here. And the blue is like way more powerful than the green. The red has very little power. It's on a low end of the spectrum, you see? This is a visible spectrum. The red is way down here. You can just barely see it. It doesn't illuminate anything hardly. Up here, it gets intense, and then you get to what's called the ultraviolet catastrophe, where the energy builds and builds and builds and builds and builds, and all of a sudden it drops right off. And that's because no more white particles are left. They're spinning so fast, you threw them all off, and all you got left is the black. That's the way I'm taking it. So here they come in. Here's the red. It's coming and spinning like this, and you can see. You see the black is in front here, and now the black is in here. It's just spinning as it comes through because they charge up. This one got charged up and flipped to the back. Now this one's going to get charged up and flipped to the back, and that's what they do. They call it the muon wobble. And these are just getting ready to get charged up. Now, so that's the red. All right, I mean, you can't miss it. There they are right there. All right, now the green is identical, and you see they even has little spikes coming up this. And I think the spikes get more intense as you get closer to impact zone. Now here's the green, right here. All right, it's coming through the Venturi, or getting ready to go into the Venturi. I'm not sure, to be perfectly honest with you. But these are the neutrinos. I think it's just getting ready to go into the Venturi. And here's when the photons show up. The other one I know 100% certain that the red was just getting ready to go into the Venturi. All right, because here's the Venturi right here. And it was going this way. And I can show you the red highlighted. And you can see it right here? Again, I showed you this, I'm sure, but that's okay. That particle is going this way. This is the energy levels within the particle. It's banging into fields that are in the gases that it's got to go through. This is light, is a particle. It's got to move everything out of the way. And it's got a field around it. So as it whacks, this one gets bigger and bigger, but it can get smaller and smaller. And at the Venturi, it seems like it can just squirt down and go through. I mean, not all of it goes through, but the majority goes through. You see here? Here's when it comes through the Venturi, right here. So we're accelerating it here. Zip. Right here, it starts to show up as a photon. So we know that's the particle. And they do show this as a photon. They've seen these. And then the two particles split, which gives you electron showers. Here's the electron showers. Now, why is this important? What's the big deal? So what, Roger? So what? Big deal. Well, remember we talked about the car didn't gain any weight. Well, you saw the atomic bomb blast. It didn't knock the house over. It just burned it up. But that's where all the energy was. And that's what makes a car run. This right here, my friends, is the energy. It's separated the black from the white. When you do this in a generator, and I know this for a fact because that's what I was in the Army. Well, anyway, I serviced Nike Hercules missile sites, and a lot of it was, off-site generation of precise power and all that kind of stuff. When you generate electricity, you are literally ripping the white particles out, away from the black, and this is a strong nuclear force. Don't let anybody tell you there's a weak nuclear force. It is. There is not weak. When you rip that electron out of there, it takes literally tons of energy to pull it out of there. That's why when you turn on a generator in your house, you lose power. You disassemble, cut off it from the main source, so you don't electrocute somebody working on a pole. And then you start up your generator. It's running. Okay, so now you go and you turn your breaker back on. So here's your generator running. And you turn the generator on. And it'll just keep doing it. Well, what is it doing? It's sending off pulses as one field hits the other field. It just forces the electrons off, but they push back very hard. So the motor, which is the gasoline motor, has to go, and it just push as these fields. Well, hold on a second. I got one here. Hold on. Okay, the easiest way to do this is the easiest way. The white we want to just push into the battery. It has no weight whatsoever. This divides it and keeps it apart. Now, how else could we divide the black from the white? Because we want the black to stay here and we want the white pushed into the battery. Well, we could do it with a motor generator. Now, this is a motor. Normally, you would put electricity into this and it would zzz. Now, if I spin it, it's going to become a generator. Watch here. I don't know if you can see that. Whoops, come down a little closer. You see, I'm on only a 2-volt scale. DC, this is direct current from this little motor here. Now I'm just going to spin it by hand. Now watch what happens. Now if I spin it to this way, you see, anytime it flashes over 1,000, it means it's over scale. See, 1.3, 1.8. It's always negative. You see it? Negative, negative, negative. Now, what if I spin it the other direction? No more negative. You see it? So I'm spinning it this way this time. No negative. Now, I'm going to spin it the other way. It's negative. So it goes either way. And what we're doing is we're pushing a field against magnets. And here's one of these motors opened up. All right, so you saw this one. And we spin it here, and it makes electricity. Positive, negative, it depends on which way we go. When you put electricity into it, it spins as a motor. So it's a motor or a generator. It does both. Now, how does it work? Well, those are some magnets in here. You see this? All right. They push against the electricity that's going through this commutator, all right? There's brushes on here. This is what's called a brush box. It fits on here, this thing here. And it has brushes that rub up against that that commutator, and it makes it energize and pushes it away from the magnets, and that's what creates a motor. If you spin it by hand, it pushes the electricity back and makes a generator. So it's one way or the other. It's the same device. And then you have AC and so forth. I'm not going to get too deep into this, but all we want to do is push the white particles in. They have no weight whatsoever, as I showed you. There's no weight. The car stayed the exact same weight. So I'm going to leave it at this, but with some very, very simple little things, little charts and so forth, and your periodic table and all these different constants and things that we can talk about. Very simple stuff. You can do a lot. This here, nobody's been able to figure this out for 150 years. I know exactly how it works and why it works the way it does work. And all of this can be explained with the dipole electron flood theory. It's the only way it can be explained. They can't account for gravity. They can't account for dark matter. They can't account for the global warming. They can't account for the sun's corona. All of these things are very simple to understand once you understand dipole electron flood theory. Very simple after that. So I guess I'm going to have to leave it at this for now. Hold on a second. Alright, this only takes like 3 minutes to read through the whole new theory. It's simple. It's just they're all dipoles and they push the black to the center, and as they get further and further away they get less and less energy. Case closed. And they can be gigantic because of these number of particles that are in what we thought were these tiny little particles. They're not. There's just thousands and thousands and thousands more particles, and these are what the particles are, and there's going to be some changes. Redshift, space, chemistry, even chemistry is going to change. And I was hoping that Professor Dave, who says he can explain everything, would discuss this with me. Maybe I'm wrong, but I'd like to show him my evidence and see what he thinks of it. So I'm sort of confronting him because he's asking, and I asked everybody to confront him, to send something to him. It says, Professor Dave explains at gmail.com, and I'd like to have him discuss this with me. That's all, respectfully. If it works out that way, if not, I could take it. You could beat me up. I'm not. I got no problem with that. Some people just like to be combative. That's okay, as long as I get to say my say. You can be combative. And I got combative for a while. It doesn't work. It didn't work for me. I don't know. Anyway, this is it. I suppose that's it.